Our lesson today deals with strength of acids and bases, and we'll be talking about strong acids versus weak acids, strong bases versus weak bases, complete and partial ionization of bases and acids, and we'll be introducing acid-base neutralization equation. Acids are molecular compounds and are therefore formed by covalent bonds. Normally, molecular compounds do not ionize when dissolved in water, but if a certain bond within a molecule is highly polar, it is possible that a molecule may ionize when it dissolves in water. So we're looking now at strong acids and bond polarity. As can be recalled from previous lessons, whether or not a covalent bond is polar depends solely on the electronegativity difference between the two bonded atoms. Here we're showing you the electronegativity values of the two bonded atoms in hydrogen. There's no difference between them, and same thing for chlorine here, because they are homonuclear molecules. Now here these diagrams are showing you how there's even distribution of electron cloud between these two atoms. Same thing here, and that's why they are nonpolar. When you bond hydrogen and chlorine to form hydrogen chloride molecule, as you can see here, there is a big difference in electronegativity values between the two bonded atoms. There's 1.4 difference there. As such, this bond will be polar and the molecule also will be polar. The more electronegative atom pulls electron toward itself, so it acquires a small negative charge and it leaves the other end with a small positive charge. This figure here is trying to depict for you what happens in a single hydrogen atom. See, right now this nucleus is well neutralized by the electron cloud that's evenly arranged around it. If something happens where electron cloud is pulled towards the right, then this positive charge manifests itself as a small positive charge in that end. Because of the greater degree of electron cloud going that side, this side acquires a negative charge. If the electron cloud separates itself from the atom, then you're left with the nucleus all by itself here, and the electron goes over here, okay? Something similar is happening in the HCl molecule. We've spoken about this already, but we're just reviewing this because we're talking about why this guy will ionize. This is HCl. You can see chlorine is pulling a greater share of the electron cloud towards itself. As such, it acquires a small negative charge here, and it leaves that with a small positive charge there. Now, what can happen here is that if hydrogen chloride gas is dissolved in water, water allows it to ionize. So here's hydrogen chloride gas. It is neutral. If you pass that through water, it ionizes, and what is produced is called hydrochloric acid now. So here you're seeing that chlorine is having 7 electrons, right, by itself. If it takes that one electron away that originally belonged to hydrogen, then the hydrogen becomes ionized and the chlorine becomes ionized too. So hydrogen ion, and this is what we call a proton. And this, of course, in your previous lesson, we said that this causes acidity and that you have a chloride ion with octet there. So this is why hydrogen chloride gas is neutral in dry air, but when you bubble it through water, it becomes hydrochloric acid. Note it is called hydrogen chloride here, and now it becomes hydrochloric acid there. You have to put in these little subscripts here to indicate the state of the gas. Inside it is in water now, so when it is in water, it's called hydrochloric acid. So this is how hydrogen chloride becomes an acid. When it's dissolved in water, the more electronegative chlorine atom takes the electron away from the hydrogen, and ionization occurs. Arrhenius, if you can remember, found that acids such as HCl are very good conductors of electricity. So if they're good conductors of electricity, it means they must ionize completely in water, because we said that it is the ions in an electrolyte that are responsible for the conduction of electricity. So this is a little table showing you here the initial concentration of HCl, hydrochloric acid. That's initial. Initially, you don't have any of these, all right, because it didn't ionize it. Finally, as it ionizes, you won't have any HCl molecules remaining, because They all ionize to give you chloride ions and hydrogen ions. So this was the initial, and these are final concentrations of your chloride and ion ions. It's like having, let's say you have 100 pairs of magnetic marbles where you have white marbles are bonded to red marbles. Initially you have 100 pairs, but if you separate them, you're going to have 100 white marbles separate and 100 red marbles separate. So there's complete ionization. When there's complete ionization or complete reaction, you notice that we put an arrow going like that, okay? You'll see a double arrow coming sooner or later when there's incomplete ionization. Arrhenius also observes solutions of some acids, such as ethanoic acid, or you call vinegar, and formic acid, and so on, conduct electricity poorly. He theorized for poor conductivity, there must only be few ions present in these solutions. This is what will happen if the acid only partially ionized. And because they only partially ionize, they're said to be weak. Why? Because they're not producing a large concentration of H plus ions. And this table here is trying to show you what is happening again. This is ethanoic acid, okay? And we pointed out to you already that that is the ionizable hydrogen there. These are bonded to the carbon. They can be ionized, but because this OH bond is polar, this can break away and form H plus ion. So initially we have all molecules here. And of course you wouldn't expect to have any of these. But as it ionizes, look what happens. You have that number of moles per liter remaining compared to these. So there's poor ionization. So look, this is the initial concentration. Now you still have lots of these here. All of that remains, okay? But we only have small concentrations of hydrogen and ethanoic ions. That's why you're going to see this sign here. This sign here means that the reaction is reversible. So how can we put that in perspective? Another way of putting that is say that this acid is only 1.3% ionized. In other words, if we have 1,000 molecules of ethanoic acid, in the end, you have 987 remaining, and these number here of hydrogen and ethanoic ions produce. So for every one of this all, you have a low concentration of that. The acid must be very weak. If an acid is weak, therefore, you won't have so many ions inside. And what do you expect of its conductivity? Would it be high? Mind you, the ions are responsible for conduction. It's going to be poor conductivity. We have a conductometer here. There's a bulb here. You can see it lights up brightly here. See that? And this one here can see how dull it is, okay? That means that acetic acid there conducts electricity very poorly. So we are saying is that compare hydrochloric acid with acetic acid. We say hydrochloric acid is a strong acid and acetic acid is a weak acid. So this is a little quiz I give my students here. What are the differences between 1 mole per liter acetic acid and 0.1 mole per liter HCl? What are some of the differences? First of all, in terms of its concentration, acetic acid here will be 10 times more concentrated HCl. Even though this guy is 10 times as concentrated as HCl, it still remains a weak acid because it is poorly ionized. And if we put a pH meter into both of them, pH is a measure of the H plus ion concentration in a solution, we're going to find you have a higher H concentration here and a lower pH. The higher the H concentration, I'll do that later on, the lower is the pH. Hydrochloric acid at all times will have a lower pH than a weak acid such as acetic acid. So these are the three differences that you have there. Conjugate base strength. All right, let's watch this now. Remember the last time we talked about conjugate base? If this is the acid, when it ionizes, what's left of it is its conjugate base. Why the conjugate base of a strong acid is weak? Look, it's acting as a base in the reverse reaction. In the reverse reaction, now look what happens. This guy is trying to push its proton onto this. But it doesn't want it. It's very reluctant to take that proton. The fact that this doesn't want to take up that hydrogen there is a weak base. Look what happens here now. This is now representing the partial ionization of acetic acid. This is the hydrogen that breaks off because of that polar OH bond here. That's why anytime I do this acid here, I always highlight the hydrogen that is ionizable. These will stay all by themselves, and that will be your acetate ion there, and this is a conjugate base. Watch this. In the Ford reaction, the ethanoic acid is unwilling to produce hydrogen. In the reverse reaction now, where this guy is going to try to donate the hydrogen to that one, the ethanoate ion is willing to accept the H plus ion. That's why it is now going to go and form acetic acid, where this is 98.7% in solution. So because this is willing to accept that proton, we say, so 2 points. A strong acid has a weak conjugate base, and a weak acid has a strong conjugate base. What we talk about now, we're going to compare a strong acid with a weak acid. So strong acid, weak acid. In terms of electrical conductivity, because of the high degree of ionization of strong acids, there will be lots of ions in the solution there to conduct the electricity, as opposed to this one here, where there are few ions to conduct electricity. So you have high conductivity here and low conductivity here. Degree of ionization, same argument, I said that already. High degree of ionization, low degree of ionization. pH of this is going to be low because it's negative log of the hydrogen ion concentration. This is going to be higher. Conjugate base, weak. Conjugate base, strong. This table here summarizes most of what we've spoken about already. Strong base versus weak base. Something similar to that is happening here. When you have a strong base, initially, you have 0 of these, 0 of these. But when it does ionize, see, you don't have any of these remain because it's completely ionized. So you have exactly 1 mole per liter here and 1 per liter here. We say this is a strong base, complete ionization. There are others which only partially ionize, like ammonia, for example. We react with water, give ammonium ions and OH ions there. Again, you're seeing this here, indicating to you partial ionization. Acidic hydrogen in acids. When you look at the formula of an acid, you can identify the acidic hydrogen. This one here will be the acidic hydrogen, this will be acidic hydrogen, and this will be acidic hydrogen here. Here you see each of these here is having 1 mole of hydrogen per mole of acid. And because of that, we call these monoprotic acid. Okay, so these are capable of ionizing to produce 1 mole of H plus per mole of acid. Even this is a weak acid, it can produce an entire mole of that, because what should happen? If you try to neutralize that acid with bases, it reacts with this guy here, the base will produce this, and it forms water. The H and the OH really are water reacting. So when you start removing these guys, it shifts the equilibrium this direction to produce more H plus, and you have more of these guys to react with them. They continue to give water. Eventually all of this will shift in that direction and it'll be completely neutralized. So never mind this weak acid. If you have 1 mole of acetic acid and say 1 mole of sodium hydroxide, which has 1 mole of OH, it will eventually neutralize this whole thing, as I have explained that to you. Diprotic acid, this is H2SO4. You can see there 2 H's there. So diprotic acid is capable of producing 2 moles of H plus per mole of acid, okay? One thing to know, however, is that these acids ionize sequentially. First of all, this H2SO4 ionizes for us to give 1 mole of hydrogen and 1 mole of hydrogen sulfate ions. Then this one now will ionize further to give you another mole, and then you get a mole of sulfate ion here. Triprotic acid now, these have like phosphoric acid, you have 3 moles of hydrogen there, and again, this is a weak acid. That's why we're showing you these double arrows here. It produces that, it's left with that. Note how you have 1 negative charge because 1 hydrogen is lost there. This one produces another mole of hydrogen. And finally, that gives you this one, So you have all three here. It doesn't happen so easily. In fact, if you were to put phosphoric acid in water, you will never find these ions there. You'll only find a bit of that and a bit of that. It's a very, very weak acid. But again, if I have 3 moles of NaOH and I drop it in 1 mole of phosphoric acid, because you're having 3 moles of OH ions here, eventually all 3 of these get neutralized and you form sodium phosphate. Look at the point I'm making here about this acid, like sulfuric acid, for example. If I drop in 1 mole of sodium hydroxide in sulfuric acid, because here you're having only 1 OH here, and that will be capable of neutralizing 1 mole of H plus ions, so you get water there, but 1 mole of hydrogen is still left in the salt here. This salt is said to be acidic because you put it in water, it can ionize to produce, this hydrogen can come out of solution there and make the solution become acidic, okay? This guy here now ionizes to give this one here, see? But this one here now still has that H plus locked up inside it, okay? It partially ionizes, you see double arrow there? It's only 20% ionized. The second hydrogen is only 20% ionized. First hydrogen is 100%. Second hydrogen for sulfuric acid is only 20. But put another mole of sodium hydroxide inside, it neutralizes it completely. So the summary equation will be what? 1 mole of this, because a diprotic acid will take 2 moles of sodium hydroxide and for complete ionization. Hydroxide ions in bases, guy is a monoprotic base because it has 1 OH, and any monoprotic acid is capable of neutralizing it. It has 1 OH, okay, because they're capable of neutralizing 1 mole of a monoprotic acid. Next, another example, MgOH has a 2 there. We call that a diprotic base because it's capable of neutralizing 2 moles of a monoprotic acid. So this is when you balance the equation because of that 2 there, right? Calcium hydroxide is another example of a diprotic base, and it is capable of neutralizing 1 mole of a diprotic acid, as shown here. So 1 mole to 1 mole, and complete ionization there. And here you have some nice questions there for you to practice your skills based on what you've learned. These are repeated in the your solutions manual. The answers are there. Okay, explanation of the answers are there.